Hi, everyone. My name is Ms. Chakiris, and I teach AP Environmental Science at Marlboro High School. And I'm going to be doing these recordings for you for the summer assignment. Um, the presentations that I'm going to be using for you guys are created by Jordan Dishinger-Smeeds. He's an amazing AP Environmental Science teacher, and his stuff is clear and concise and to the point, and he's got a great YouTube page, and he has a great Instagram, and he also did a review on TikTok for the APES exam this year. So this is Unit 1, Part 1. We're going to go over ecology and ecosystems, which should be review for everybody from biology. The way that these presentations are set up is that every unit has a whole bunch of different subsections. So for Unit 1, this is 1.1. It's on ecosystems. Here are your learning objectives, your essential knowledge, and the skills that you'll learn during this unit. So ecosystem basics. What you have here, let me move this. We start small and we go up, whereas biology is you start small and you kind of go even smaller. We start at an organism and you go up. A bunch of organisms is a community. There we go. Or a population, sorry. And then you have your community, which is all living organisms in an area. And then your ecosystem, which is your living and your non-living things and all of them kind of interacting. That's ecology. And your biome is the larger area with your similar climate conditions. And that really determines what plants and animals will live there, like a tropical rainforest. And here we have organism interactions. You have competition, predation, mutualism, and commensalism. And you can see here that species will either be positively impacted, negatively impacted, or really the zero is meh, it really doesn't have an effect. So your competition, organisms are going to fight. They're going to compete over something for some sort of a resource. Food, shelter, this limits your population size. Predation, one's going to eat another one. Even herbivores, they eat grass. Mutualism, both benefit. We're going to take a look at some of those. And then your commensalism, one organism benefits and the other one's like, oh, hey, I didn't know you were there. You have no effect on me whatsoever. Predation, you have herbivores that are also predators, and then true predators, which are carnivores, they kill and they eat their prey. But you also have parasites, which are predators. Mosquitoes, tapeworms. This picture is of a sea lamprey. And what they do is they end up boring into the skin of fish and kind of sucking the guts out. They're fun. And then you have parasitoids, which lay eggs either inside of a host organism or on top of a host organism, so that when this organism, a parasitic wasp, let's say, hatches, okay, that's a parasitic wasp. It's laying its eggs on this tent caterpillar. And you end up getting, when they hatch, they have a food source and they kind of eat the caterpillar to death. Nature is a funny thing. Symbiosis. Any close long-term interaction between two organisms of different species. You cannot have a symbiotic relationship within two of the same species. You have mutualism, commensalism, and parasitism, all symbiotic relationships. Mutualism is both benefit, like corals. They provide the reef structure for carbon dioxide for these algae, and these algae provide sugars for coral to use as energy. You have lichens. Lichens are obligate mutualism. So what happens, I wonder if I can move this off. Interesting. So it's a symbiotic relationship between a green algae and a fungi. But the thing is that without the fungi, it's not a lichen. Without the green algae, it's not a lichen. So you need them both together. Same thing with corals. They won't survive without their algae. So here's a lichen. Competition. This reduces your population size since there are going to be fewer resources available. So what happens is organisms will partition a resource. So you have this resource, everybody wants to use it. So they use a resource in different ways to actually reduce coming in contact with each other, to reduce that competition. So we have temporal, spatial, and there we go, morphological partitioning. So your temporal is the top up here. Your coyote and your wolf, they are going to use the same species resource, but they're going to hunt at different times. The wolf is going to hunt during the day. The coyote is going to hunt at night. Spatial is using different areas. All of these birds want to use the tree, but they can't use it at the same spot at the same time. So they all want to use it during the day. So basically what happens is these ones go over here, these ones go over here, these ones go over here. So that is spatial. So they're spatially partitioned. And then morphological is using different resources based on different evolved body features. Okay, so it's like a beak size of finches of Darwin. You know, the bigger beak size are going to eat the bigger fruits, whereas the smaller beak size are going to eat the smaller fruits. And here is an FRQ for you guys. Moving on to the next part, primary productivity. Here are your objectives, your essential knowledge, and your skills. So primary productivity basics. This is the rate that solar energy is converted into organic compounds via photosynthesis over a specific unit of time. So you have kilocalories, which is the energy. You have meters squared, which is the area. And then you have year, which is the time. Your energy, your area, and your time. There you go. So your rate of photosynthesis of all producers in an area over the given period of time. So since photosynthesis leads to growth, you can also think of primary productivity as the amount of plant growth in this area over this time. So when you have high primary productivity, you have high plant growth, you have lots of food, lots of shelter for animals, you typically have a thriving organisms. So these ecosystems with high primary productivity are usually more biodiverse and they have more biomass than ecosystems with low primary productivity. The way you calculate this is you need your respiration and you need your gross primary productivity. So with your respiration loss, this is what we're doing right now. Plants use up energy they generate via photosynthesis by doing cellular respiration. That's their movement, internal transportation, etc. So if we're taking a look at this when it comes to like you having a job, you do your job and you get paid for it, but you need to pay taxes. Okay? Your gross primary productivity is the total amount of sun energy that it takes to do everything you need to do, and then everything to convert your glucose, your energy into glucose through photosynthesis. And then this is the whole thing. Okay, you get paid $10 an hour. You work for 10 hours. You should be getting $100. This is your gross primary productivity. And then what happens is Uncle Sam comes in and he says, no, we're going to take out taxes. That's your respiration loss. And then what you end up getting is your net primary productivity. Right? You end up getting paid like $80. That's what you end up taking home. You got to run around and, catch your money with a net. So your net primary productivity is the amount of energy or the biomass, the weight, the stuff left over for consumers after plants have used some of that for respiration, your respiration loss. So your net primary productivity is your gross primary productivity minus your respiration loss. It's a fun picture. Ecological efficiency. Incoming solar energy is captured by plants and converted into biomass, right? Net primary productivity or food available for the next level of consumers. So if you see over here, 99% of the solar energy is actually reflected or it passes through producers without being absorbed. And 60% of it is lost to respiration. So that's your respiration. And then your net primary productivity is that 40% that supports the growth and reproduction of these producers. This is your net primary productivity. This is what is left over because the majority of the solar energy is reflected, and then the majority of what actually hits the plant is actually lost to respiration. So some ecosystems are more efficient. They have a higher net primary productivity than others. But the more productive a biome is, the wider the diversity of animal life it can support. So what you guys are going to do here is you're going to try to predict the most and the least productive terrestrial and aquatic biomes. Okay, so terrestrial means on land. So those would be your continental ecosystems, and your aquatic ones would be marine ecosystems here on the bottom. So these are the ones you have to choose from for most productive, and these for aquatic, and these are the ones that you have to choose from for most productive for terrestrial. So your coral reefs, your salt marshes, your swamps and marshes, and your tropical rainforests are going to be your most productive ecosystem. And water availability, higher temperature, nutrient availability are all factors that lead to a high net primary productivity. Any of those factors that you don't have enough of, they're going to lead to decreased net primary productivity. They're going to be limiting factors. So like desert scrub, tundra, they have your desert has low water and low nutrients. Tundra has low temperatures and liquid water that can't be taken up by most of these plants. Open ocean has low nutrients. It's this big, vast, open, almost nothingness in a lot of places. So here are your FRQs for this little section. Trophic levels and the 10% rule. These are the last two that we're going to cover here. Here are your objectives, your essential knowledge, and your skills. Conservation of matter and energy. So matter and energy are never created nor destroyed. They only change forms. Trees die, the carbon, nitrogen, water, phosphorus are returned to the soil and into the atmosphere. It doesn't just, okay, it ceases to exist. Those nutrients are recycled. That energy changes forms. It's not recycled. Sun rays, they hit the leaves, they're converted into glucose. So the energy comes from the sun and then it's being taken in. And through the process of photosynthesis, it's being turned into glucose. The first law of thermodynamics says energy is neither created nor destroyed. And biogeochemical cycles, which we're going to get to in the next one, they demonstrate conservation of matter because these nutrients cycle through bio, okay, the organisms, living stuff, geo, the earth, and chemical. These are chemical cycles. Food webs demonstrate conservation of energy. When a rabbit eats a leaf, energy from the leaf is transferred to the rabbit and it's stored as body tissue like fat and muscle, and they use that for their metabolism. We do as well. Second law of thermodynamics says each time energy is transferred, some of it is lost as heat. And this is your 10% rule that you get. If you're looking at this to calculate efficiency, you have, let's say, a coal burning power plant. 35% of that coal is actually converted into electricity. About 65% of it is lost as unusable heat energy. And then what happens is when you have your light bulb, okay, you plug in your light bulb, there's 90% of the energy from the transmission lines ends up coming to your light bulb because energy is constantly being lost. And then you turn on that light bulb, and these old incandescent ones, we have more efficient ones now, you have most of it comes off as heat energy. 95% of that light bulb is burning as heat, and only 5% of it is as light energy. So if you calculate it all the way from the beginning, you actually have a 1.6% efficient light bulb. That's why we have other things now. When we apply this to food webs, the amount of usable energy decreases as you move up the food chain. So if you take a look here, you have 1,000 joules of light energy coming into this plant. 10% of that is available for food. So 10% of that passes up to the next trophic level, okay? Because 990 joules is energy that's lost in the environment. So now this 10 joules can be passed to the next trophic level. 9 joules of energy is lost in the environment, and only 1 joule remains for this lion to eat. So this 1 joule of energy goes into the lion, and 0.9 of that joule is energy lost in the environment. And then if something were going to eat the lion, or what is available to the lion then to move on to the next trophic level, is 0.1 joules of energy available as food. We can show that in a food chain in a minute. But available energy, okay? Available energy decreases with each step up the food chain or the trophic pyramid. And a trophic pyramid is used to model how the energy moves through an ecosystem. So here we go. You have your producers, your primary consumers, and these are your primary producers. You have your secondary consumers and your tertiary consumers. Now, if you're talking about trophic levels, this is your first trophic level, this is your second trophic level, this is your third trophic level, and this is your fourth trophic level. So your primary consumers are actually on your second trophic level. So we call this the 10% rule. About 10% of the energy from one trophic level actually makes it to the next. The other 90% is used by the organism for their metabolic functions and lost as heat energy. So here, as we move up, 90% is lost as heat energy, 10% goes up to the next. 90% is lost, 10% goes up. 90% is lost, 10% goes up. So here you have your producers on the bottom, your plants, your autotroph, they convert sun's light. You have your primary consumers, your herbivores basically, your secondary consumers that eat your primary consumers, and then your tertiary consumers up top here. Okay. This also applies to biomass or mass of all things living at each trophic level, not just energy. So energy is needed for growth and 10% transfers from one level to the next. 10% of the biomass is only grown or supported basically. So you're going to end up, if you're not eating enough, you're ending up losing weight. That's the whole premise of it. All right, so here, if you have 1,000 kilograms, we're talking about biomass, 90% of that is going to be lost and 10% is going to go up. The easy way to do this is you lob off a zero. 100 kilograms is left at the next level. Then you go up to 10 kilograms and then to 1 kilogram. What you guys are going to do now is you're going to calculate the biomass or energy available at the next trophic level. Okay, you move the decimal place to the left, or you divide by 10, or you just dismiss one of those zeros. So if these producers have 95,000 joules, what you're going to do is see how many joules are available for the primary consumers, the secondary consumers, and the tertiary consumers. Okay, so as you see, you have 9,500, you have 950, and then you have 95 joules up top. We could do the same thing with biomass and energy, or biomass, sorry. So here you have your secondary consumers have 80 kilograms. So go ahead and fill in your tertiary consumers, your primary consumers, and your producers. You have 8,000, 880, and 8. So then here are going to be your practice FRQs for this unit. All right, and then we have food chains and food webs. Here are your objectives, your essential knowledge, and your skills for the unit. Food web basics. These show how matter and energy flow through an ecosystem from organism to organism. So when one organism preys on or eats another, the matter, so all your carbon, your nitrogen, your water, your potassium, and all of your energy, your glucose, your muscle, your tissue, etc., are passed on to the predator. And the arrows in the food web indicate the direction of energy flow, is eaten by. The organism taking in the energy, it's pointing towards it. That's the way the energy is flowing. A food web versus a food chain, you can see the food web is very simple and the food chain is a bit more complicated. Food webs have at least 2 different interconnected food chains. So you see here, your grass is eaten by the rabbit is eaten by the fox. The grass is eaten by the grasshopper is eaten by the mouse is eaten by the fox. So you can actually have organisms occupying different trophic levels. So for here, you have this fox. So this would be your first trophic level, your second trophic level, your third trophic level, your fourth trophic level. Whereas over here, it would be your first trophic level, your second trophic level, and then your third trophic level. So it's not like everything is set. And these organisms can exist at different trophic levels. Cool. Interactions in trophic cascades. A trophic cascade is crazy. A cascade is a almost like a big waterfall that just kind of whoosh, and it flows down. And if you increase or decrease the population size of a given species, it can impact the rest of the food web. So if you were to increase the python population over here, okay, their population increases. They're going to be more of them, so they're going to need to eat more food. So what's going to happen is your frog population and your rat population are going to go down. So now you have less rats and you have less frogs because there are more pythons. And since there aren't a lot of rats or frogs, your grasshopper population is actually going to go up because nothing's eating them. And now with an abundance of grasshoppers, you actually have less corn because grasshoppers eat lots of corn. So that's your trophic cascade. And it happens typically when you take your top predators, like your keystone predators, out. Okay? The removal or addition of a top predator, it has that ripple effect down through the lower trophic levels. Very famous case study with wolves in Yellowstone. What happened was they had the wolves, the elk, and the trees. And what happened was they removed all of the wolves. The elk population increased, and they ate all of the trees, and our forests really started to decline. Well, their forest started to decline in Yellowstone, but in New Jersey, we have big issues with deer. And the deer are destroying our forests because there are too many deer. There aren't any natural predators except for cars. Those aren't natural. And what happens is they're eating all of our saplings, the young trees in our forests, and we're having some big forest issues in New Jersey, which is why we do controlled hunts and have sharpshooters in parks, especially in North Jersey, that will close the parks for a couple of days and will herd all the deer into a certain area so that we can have thriving forests again. And then here is your practice FRQ. Move my face up here. For 1.11.